ഇത് രണ്ടും ഭയങ്കര എഫക്റ്റീവ് ആണ്. കമ്പയർ ടു റിസോഴ്സിനോ ഹൈഡ്രോക്യൂറിനകത്ത് കുറച്ചുകൂടെ എഫക്റ്റീവ് ഉണ്ട്. അപ്പൊ ഞാൻ ഒരു സീക്രട്ട് ആയിട്ട് ഒരു ക്രീം സജസ്റ്റ് ചെയ്യാം. അപ്പൊ ഇത് റിസോഴ്സിനകത്തുണ്ട് നമ്മളെ മെലാനിൻ റെഡ്യൂസ് ചെയ്യാൻ.
Ravikumar sir, am I audible?
Yeah, 1 minute. I'm going to give the permission to sir. Yeah.
Okay.
I think sir can switch on his mic and sir can open his video also. Ravi Kiran sir, please switch on your mic. Ravi Kiran sir, hello. He joined, I think.
Yeah, he joined actually.
Hello.
Yeah, Ravi Kiran sir, please.
Can you hear me? Am I audible?
Yeah.
Yes, sir.
Sir, please switch on your camera, sir.
Yeah, I am trying to, but there seems to be...
No issue. No issue, sir. I think I think you can share your presentation, sir.
Yeah. I just want to confirm that I'm audible, right? I'm audible.
Yeah, you are audible,
yes,
sir.
Yes,
I give the permission to share your presentation. You can share now.
Okay, all right. So I will just begin. Just give me a moment, please.
Yeah, meanwhile, I'm requesting to Dr. Sitaram, please introduce about Dr. Ravi Kiran sir. He's from IIT Hyderabad.
Yes. So, good evening, participants. So, next session is that robotic vision by the Dr. Ravi Kiran. Dr. Ravi Kiran is Sarvapatla is an associate professor at Center for Visual Information Technology at IIT Hyderabad, where he has been serving since 2018. And he also leads the mobility related to applied projects and academic programs at iHub.data. And Dr. Ravi Kiran is earned his PhD from IIC Bangalore in 2018. And his doctoral thesis received the prestigious IUPR AI Best Thesis Award and the Sir Vital Chandarwarkar Memorial Gold Medal. Prior to pursuing his PhD, he worked with US-based R&D companies from 2018 to 2013, and he completed his MS in computer science at the University of Washington, Seattle, USA in 2008. Dr. Ravi Kiran research interests are broad and interdisciplinary, focusing on problem solving, multimodal, multimedia data such as image, videos, text, and audio. So he works a span diverse discipline, including graphics, robotics, and human computer interaction. So I welcome sir for today's session. So thank you, sir, for joining this session, and you may continue this session.
Okay. So thank you, Dr. Sitaram, for the introduction, and thank you, Dr. Ravi Kumar, for your invitation to this session. I'm very pleased to be here. So I will share my screen and get started. Please let me know once you can see the screen.
Yeah, we are seeing your screen, but not presentation, sir.
Yeah, so I am going to start the presentation. Please let me know once you can see the presentation itself.
Yes, sir. It is visible. Yes, sir. Yeah, you can continue.
It is visible. You can continue.
So today, instead of one specific topic, what I'm going to cover is a number of ways in which robots and vision come together. So in today's session, we will see how different kinds of problems in practical settings can be solved using a combination of special robots and some camera based system which is attached to such robots. I will give a brief overview of some of these projects, and hopefully that will give some flavor of how these things can be put together for various applications involving robots and using vision. So the first work I will talk about is on infrastructure assessment using drones. So what do we mean by infrastructure? So you can think of infrastructure as basically any kind of civil structure. It can be a building, it can be a bridge, any such infrastructure, electricity poles, etc., are what we commonly refer to as infrastructure. And there are many scenarios where this infrastructure needs to be assessed. So here assessment means we want to measure some property of that infrastructure. For example, if there is a bridge, then we want to make sure that the bridge is in good condition. If there is a building, we want to make sure that the building is structurally sound, and that all the parameters required for safety and its well-being are being met, and so on. And if there is, say, some kind of electricity utility pole, then we want to make sure that the light is working or it is not rusting, and so on. So in order to do this, previously people used to do this manually. So in an era before all these automated methods came into the picture, people used to go from place to place. So they would inspect the structure manually and make note of various defects that were there, and then prepare a report. Now this is very tiresome and it is very laborious. You can imagine trying to do this for a large building or a large bridge. It involves a lot of people. It is very tiring. It is prone to fatigue, so people can make mistakes. So how do we do these things in an automated manner? So in this presentation, we will look at how to use drones for a specific kind of infrastructure. In particular, we are looking at buildings. Now, generally when there is a building, there are some inspections that are done. And one such inspection is to see how vulnerable the building is to earthquakes. So after the building is constructed, and periodically after construction, building inspectors, government appointed building inspectors come, and they fill a form which looks like what I'm showing on the screen. So these are some of the parameters in the form. So they want to find out what is the planned dimension of the building, and how many stories are there. Is it a 3-story building, 5-story building, and so on. And then they look at things that can cause threat to these buildings. For example, presence of buildings which are very close, other buildings which are adjoining and which are very close. What is the distance between the buildings, and are there any heavy items on the building? So these are all parameters which must be measured so that we can understand what is known as seismic risk, basically the risk of the building to earthquake. And so they give a score for each of these items which are filled. So item number 25, 52, which you are seeing, each of these they get some marks, and if the score or marks increase above a certain number, then that building is considered risky, and then some intervention has to be done to reduce that risk. So now imagine trying to do this for say a large apartment complex or a housing colony. There are hundreds of buildings, and to do this manually is extremely time consuming. So the alternate solution that we come up with is to use drones. So the plan is that we want to have a drone, and we attach a camera to the drone, and then we fly the drone near the building. to measure everything that can be measured using photographs or just from visual inspection. So we identified some parameters which could be measured from a camera which is put on top of it. So for example, how many windows are there, how many stories are there, what is the area on top of the roof, and what are the objects that are present on top of the roof, what is the distance between buildings and objects on the rooftop, and are there any cracks, and so on. So this involves some amount of image processing. So I will not go too deep into it, but I will briefly explain the procedures that are involved. So let us take estimation of windows or story parameters. So the way this is done is you make the drone start on the ground and then you fly the drone vertically up. So the picture on the left, the animation on the left shows how the data is collected. And as the drone flies up, it sees each floor. And every time it is at a particular height, every second it is taking one picture from its camera. And then we use a deep neural network which has been trained to detect windows. So given a photograph, it will draw a box every time there is a window in that picture. So this is known as object detection. In this case, the object is a window. So once these windows are identified, then we know where exactly that window is in the picture. Now, if you look at the video on the left, you can see that the window does not appear only once. As the drone flies from the ground to the top, the window appears multiple times. So now we need a way to count the window only once. We don't want to say just because the window is coming for 4 seconds, there are 4 windows. That is not true. So therefore, what we do is we perform stitching. So for those of you, you have used this feature in your camera, there is something called the panorama mode, pano mode. So you can slowly move your phone and you get a picture like the one that is shown here. So you get a panoramic picture. And in this panorama picture, we try to take the individual pictures and map them to this panorama picture. So that way, each window appears only once. And this is now used to understand the complete profile of the building. So from this picture, we get the following idea that there are 4 windows and there are 4 stories. Now, windows, it is easy to identify. We have a neural network which identifies the windows. But how do we get an estimate of the stories? Right? So one story is basically one floor. So our way of doing it is we say that we look at the vertical distance between windows which are located in the same plane. So if you have, as this picture shows, if you look at this particular picture, so the distance between 2 windows, their midpoint is taken as 1 story. So that is one part. Now, what we really want is the distance in meters. So for this, we use a sensor on the drone which measures its height off the ground. So every time the drone flies, there is an internal accelerometer sensor which tells how high it is off the ground. So it needs to know when it has landed so that it can shut off and all that. So we access that internal sensor and then we assign each of these windows with that physical measurement. So that way we now know what is the physical height of each window from the floor in meters. And because we are saying that the height of each story is the distance, approximately the distance between two windows vertically, we can also get height of the story. So two of the parameters that we want, the count of the windows and the number of stories and the height of each story. All of these items we can get from this information. So this picture shows how the story height is estimated. And in order to cross verify this, so we build what is known as a 3D map. So from the photographs and from the movement of the camera, actual measurement of the story distance. So this table shows how well it works. So naturally, if somebody wants to use this, the first question they will ask is, how accurate is this method? Now, since much of this data was collected in our campus, we have access to the building floor plans, and we know what is the height of each story from the ground. So we have what is known as the ground truth, or the actual height, and then the height estimated using the sensors on the drone and the image information. So we see that for different stories, what is the error in the estimate of the height? So it is somewhere between 2.1 to 2.5% error. So the average error is 2.3%, which is quite acceptable. So we are within plus or minus 2.3% of the actual height of the building. So in this way, we can estimate story height and number of windows. Now, how do we get distance between adjacent buildings? Now, depending on the configuration of the building. So buildings, as we know, we sometimes it may not be possible to do this measurement directly. So for this reason, depending on the building, we fly the drone in 3 different modes. And this slide shows the 3 different modes in which the drone is flown. So in frontal mode, the drone is flown upwards and then it moves to the left between the buildings. So it starts from one of the buildings and it goes across the gap and it comes to the other side and then comes down. So this is frontal mode, and this mode is convenient to use if for some reason the drone cannot go between the 2 buildings. There may be wires or other obstacles which may pose a threat to the safety of the drone. So in that case, one can fly in frontal mode. The other mode, when it is safe and possible for the drone to fly in between the buildings, then the drone is flown in between mode. So this is the picture in the middle that you see in the slide. Finally, if both of these modes are not possible, then you can fly in rooftop mode, where you fly high above the building and then the camera is tilted downwards and you get a bird's eye view of the roofs of the building. So the frontal mode can be used when it is not possible to go between. The in between and the roof mode can be used to calculate distances when the buildings have irregular shapes. So we will see an example of that. Also, the roof mode is helpful because once you go above the building, there are no obstacles, right? Sometimes there may be trees which are close to the building and so on. So all these are not an issue when you are flying high above the buildings. So now from this, how to calculate the distance between the buildings. So again, we take the image sequence and from the image sequence, we use a similar technique as stitching, but with a little bit more computation involved to build what is known as a 3D point cloud. So the second picture you see, the picture after the image sequence, is a 3D point cloud of the entire fly area. Right? So wherever it has taken photographs, it can take that and build this 3D point cloud. And after getting the 3D point cloud, the the first step is to identify what are the vertical planes. So you want to see where are all the vertical planes, and those vertical planes are estimated for the two buildings. So the red represents the building here, the one with the semicircular structure, pipe structure, and the blue represents this particular building, the one on the left in the image sequence. So once you have this, now since this is a 3D model, you can estimate the distance between them. Now notice that between these two buildings, if they are not rectangular, the distances will vary. So from here to here, so there is no one set distance. So therefore, what you do is you take all these measurements and you take their average and call that the distance between the two buildings. So that is how we can measure the distance between two adjacent buildings. Now, the problem of roof area estimation. So over here, you can see the drone that we have used. So this is a DJI Mini SE, the drone that we use for these experiments. So for obtaining the roof area, the drone is first flown above the building and the camera is pointed downwards. And then you get a plan image. So it helps you get an orthographic view or the plan view of the entire building. So now once you have that, so this is how the image will look like from the very top. You perform some image processing so that distortions in the image caused by the camera distortions are removed. And then after that, it is fed to a deep learning model, which obtains a segmentation map, right? Like basically it marks in the image what is all the building area. So you can see here it's called binary mask. So it takes this picture and converts it into a 2D array with zeros and ones. So the 0 represents all the background, the non-building part, and the 1 in yellow, it is just shown in yellow for easy visualization. So this represents the building portion. So now in this 2D area, we can obtain the percentage of all the yellow, and that will tell us how much area is occupied by the building. Apart from this, since we know the camera parameters and the height of the drone, using triangulation, we can find out what is the total length and width in meters. So once we know that for this image, the width corresponds to some 40 meters or 30 meters. Similarly, the height of this corresponds to some 20 meters. From that, we can turn the area in pixels to area in square meters. So once we are able to do that, we get the roof area estimation. So we can estimate the total area of the roof. Now we want to again cross verify. So if we have building plan, again we can do that. But if we don't, another method is to use Google Earth. So Google Earth, if you give a latitude and longitude, the location of the building, then it will give a satellite view. So these are some of the things that you get from the satellite view. And then you can measure the area in Google Earth because it gives the scale in square meters. And from that, you can see what is the difference, the measurement obtained from the drone versus the measurement that you are getting from Google Earth. And then again, you can see what is the error percentage. So the area estimated is somewhere, the difference between the areas, actual and estimated from the drone, is somewhere around 4.7% on average across different buildings. So in this way, one can obtain the area of the roof. Now, it is also common that we don't have roofs which are empty. Often there are different kinds of things on the roof. There may be solar panels, there may be some heavy objects that are placed. All these are actually, they add to the earthquake risk. So we need to subtract them or identify them So for that, again, you fly in the rooftop mode, and the picture here, this animation shows how the drone collects the data. And from this, we pass this information to a object segmentation model, which successfully identifies, in this case, the rooftop solar panels. So you can find out how much area of the roof is occupied by the solar panels, and what are the kinds of objects that are present on the roof, and all of this information. And apart from this, we may be interested in various kinds of structures that we tend to find in buildings. So we may be interested in counting the number of solar panels, and from that we can get an estimate of the green index of that building, how much energy it may be able to recycle. It's all these measurements we can make. And similarly, we can get an idea about what kind of piping is installed. So you can segment pipes. So that is shown here, where all the red area corresponds to the pipes that are identified using a segmentation method and projected onto the 3D model of the building. So this way, we can, once we get this 3D map using the drone, we can perform a complete building inspection, and we can also try to identify different kinds of utility services. So water pipes, sewage pipes, all of those can also be tried to be identified. Now, as I said before, it is common for buildings to have cracks. After a while, they do develop cracks. Now, important thing is to make sure that the cracks are not severe. So in order to first do that, we need a mechanism which can identify cracks on the building. So for this, again, we fly the drone, and we develop a method where this photograph taken from the drone is given as input to a deep neural network, and it tries to identify the crack portion within that. And because we know the square meters that a particular patch occupies, one can measure the length and the size of the crack, the area of the crack. And from that, one can say, put cracks in different categories. So this is a minor crack, mild crack, and a severe crack. So we can see the extent of these cracks, and that can be used as some kind of a warning, or you can do some intervention to make sure that the cracks don't become too serious. So these are some images which are taken on our campus, and from different viewpoints. So you can see that it is able to identify cracks reasonably well. Now this problem is challenging because cracks are extremely thin, and sometimes if the cracks are straight, they may be mistaken for decorative structures on the facade of the building, on the side of the building. So this problem is extremely difficult to solve. But in order to do this using a deep neural network, we first collect this data, and these are labeled. The areas which have cracks are manually identified. And then we also try to analyze the performance of this method depending on distance of the wall from the drone camera. We want to make sure that we are able to identify even if the drone is some distance away, because there may be many situations where the drone cannot fly too close to the building, either for its own safety reasons or for privacy reasons. So therefore, we want to see whether the method is stable even when it is a good distance away from the camera. So this set of experiments is to analyze that, and you can see the results. Obviously, you get better quality results when you are closer to the building, but the method performs reasonably well even if it is as far as 2 meters away from the building. So this slide shows a comparison of our method with different compared to different approaches. This is a continuation of that, and essentially you can see that it is the same thing, but you are now further and further away from the building. So this is at 3 meters and 4 meters. So apart from this, we were keen to see that we have a method which works not only for building cracks, but it can detect cracks in general, because cracks appear not only on buildings, they can appear on floors, or they can appear even on roads. So whatever the kind of infrastructure we are talking about, we should be able to identify that. So we came up with a approach which is able to identify these cracks, not just in buildings, but also in various other kinds of structures which contain cracks. So its utility goes beyond just buildings in this case. And of course, there are some cases which are very challenging, and in this case, it does not work well. So, for example, if the crack is very, very faint, it's extremely difficult to, it occupies a very small portion of the image, and this makes detecting the crack or segmenting the crack very difficult. In some cases, also, the crack is too faint. If it is too faint, that also makes it difficult to identify. So in this case, it did identify a portion of the crack, but it is not complete. So this portion could not be identified. So there are still some cases where some improvement needs to happen. But for the most part, the method works quite well. So the other important factor is to make sure that the building is not tilted. So generally, a lot of care is taken to make sure that the building is not tilted. But we want to make sure that with respect to the flat ground, it is not tilted. So for that, we first develop a method to estimate tilt. So we need to know, given a structure, how tilted it is with respect to the ground. So these are a set of steps in our campus, and you can see that there is different levels of heights as you go from one level to another. And we wanted to see whether we could build a map of that structure. So that way we can say where the we can fit 2D planes, flat planes to each of these structures, and we can see if that is matching with the video that is taken of the scene. So this is hopefully this has given some overview about the ways in which we can use imagery from camera to obtain various kinds of parameters for the building. And I just want to show our project page. So one of the things we did for this project was we wanted this to be useful for civil engineers, and we wanted it to be as easy as you have a camera and a drone, and you take that video and you take the drone data and you just drop it into a folder, and then you have a software which will do it for you. So for that sake, we have developed a project page with some instructions on how to use it. So is this website visible? Can you see this? Hello?
Yes, sir. Sir, it is visible.
Yeah. So therefore, here you have the research paper. So I will not go into the details. So the research paper which talks about the details of this, and then there is the source code which can be downloaded and used, and also there is documentation on how to set it up. So for example, if you want to use this, then how do you do data collection, and how do you do installation, and how do you use this entire thing so that it is also useful, can be used by non-experts. So that has been given. The other thing that is also available is the software for identifying cracks. So that software is also available from here, both the data set and the code. So the data set is a data set of building cracks and their ground truth, and the code is takes an image as input, and it gives a binary image which identifies what are the locations in that image which contain cracks. So you can look at these resources to understand the how to use this and how to identify all these different structures of interest. So before I move on, I just want to see if there are any questions. So I can take some questions before I move on.
Yeah, Professor. Yes. Yeah, I think one person is asking the question, why it is error in the estimation.
So
yeah, please.
yes,
Yeah, please.
yeah. So we are using statistical methods, and also the measurement is not 100% accurate because of the statistical estimation methods that we are using. So that is where the error comes from. Also, in this process, the range sensors which are used, the sound-based or laser-based sensors which are used, so they have some precision. Now we can reduce the error by going for more sophisticated measuring devices or sensors, but the overall cost increases. And if the overall cost increases, then the method will not be taken up by, say, disaster agencies or government officials. So we want to make sure that we have reasonably priced equipment which they will be willing to use. So that is one consideration. And also, as long as the error is within tolerance, it may be quite fine. I hope that answers the question.
Yeah, only one question they asked, Professor. You can continue.
Okay. So I see another question. Somebody raised a hand. I don't know if it is the same person. Ramesh Babu.
Actually, they want to, actually, we are not unable their mic. Actually, there is a lot of disturbance is coming. They can post the questions in chat box and we can see also.
Okay, so then maybe we can take a minute or two. So if you can post your question in the chat box.
Yeah. I think up to now only one question it is there, Professor, that is cleared.
Okay. So I will now move to the next topic. So let me again share my screen. So I will show one more example of a scenario where robots can be used for real life applications. So now this is for warehouses. So we have all these godowns or warehouses where different kinds of items are stored, and increasingly robots are being used to navigate and work in these warehouses. So imagine that there is an inventory of items that has arrived. So one of the things that a warehouse manager has to know is where is the free space and what kind of items can be put where, and that estimate can be done only with when you have the free space. So now again, as with the previous problem, it is difficult to do this manually. So therefore, we show a method where you can have a wheeled robot, right? A robot with wheels inside a warehouse, and it can do some measurements of free space, right? So I briefly play a video which gives an overview of this approach, and we can take a look and then discuss. So just give me a moment here. So is my, please let me know if the audio is not enabled because this video in order to follow the video, you will need to follow the audio. So if while playing the video, if audio is not visible, please let me
No,
know.
at present your screen is also not visible, Professor.
Yes, I'm sharing it in a moment.
Yeah.
Okay, so is it visible, the video?
Yes. I think screen is visible. IEEE International Conference.
Right. So I will play the video. Is the audio from the video, can you hear it?
No, audio is not audible, but only
I think
yes.
it has to be enabled on your side. Can you check once? Otherwise, I will check while sharing. Maybe I have to do it. I will try once again.
Okay.
Yeah, it audio is not audible. Okay, so I will. How do I do this? Share audio. Okay, let me try this. Just give me a moment. I'm going to try again. Is it audible now?
Yes, sir. Yes, sir.
It is. Okay. So I'll continue.
Sir,
So I will
video,
explain.
video
Yes.
sound is not coming. It's not audible.
Oh, I thought it was. Someone said it was audible. No.
No, sir. Video sound is not
I
audible.
think there is a problem. I think somewhere. You can continue, Professor. By
Okay. Actually, what I will do is I will mute and I will, as the video plays, I will pause and I will explain.
Yes.
Okay.
Yeah. So let me do that. So the problem here is there is a camera mounted on a robot, and it takes pictures of the racks in a warehouse. And this is how the rack looks like. And from this rack, we want to get an idea of different things. So we want to know, first of all, what kind of items are there, how much space do they occupy. So in order to solve this problem, think about all the intermediate problems that need to be solved. First, you have to find out how many shelves are there, and then in each shelf, you want to find out what is the height of items that have been stacked. And from this, you want to build a 3D model of the rack. I mean, even we as humans, when we have to figure out whether an item will fit somewhere, we are mentally building a 3D model. It happens so fast that we don't even realize it. From that, we are able to estimate whether some physical item will fit on a rack or not. So we want the robot to be able to do the same. So in order to do this, of course, we will need access to a physical warehouse, but getting an access to physical warehouse is extremely difficult. So in this case, what we did was we used a 3D modeling software called Blender, and in that 3D modeling software, you can build different kinds of environments. So in this case, we built different kinds of warehouses, and within that 3D warehouse, you can put different kinds of racks, like the one that is shown here, and you can put different kinds of items. So you can have 3D models of rice bags or soap or whatever, any stationary items, and you can place them, and you can then take a photograph in the 3D environment so that you get these pictures. So this picture is not real, it is synthetic. But the nice thing here is that because everything is in your control, you can have as large as a warehouse as you want, you can take as many pictures as you want. So this is a good way of building, like this is a very popular approach in robotics, where you build a model first for a synthetic environment and then do what is known as sim to real transfer. So you, whatever model you develop for synthetic, you try to make it to work in a real environment. And because it is synthetic, and because we know exactly where we are placing, we know the actual 3D properties. Not only that, we also know their height and all the dimensions in the 3D world. So from that, we are able to say that the 3D reconstruction must look like this. That is, given this picture, it should be able to generate this kind of front view and this kind of top view. That is what we want the system to be capable of. Now, there are two kinds of ways of doing this. One is shelf-centric. So if you imagine that there is a coordinate system that is attached to the shelf, 3D coordinate system, and then within that you want to be able to say. The other is egocentric, that is from the viewpoint of the eye. So how does the shelf look like when I view it from this particular viewing angle? So this shows if I view it from here or from here, how does it change the appearance of the shelf? So once we have this, we set up the 3D environment, and we collect different kinds of data. So now once we are able to do that, we take a picture and we get the shelf, and we have a neural network which predicts the top view and the side view. So this shows the top view of the shelf, and this shows the side view. And because we know the actual dimensions, we can also measure, as this shows, we can also measure the amount of free space. So given a shelf, you can have a system which tells how much free space is left. So that way, if the robot is carrying an item, it can know whether that item can be placed here or not. So you can get an estimate of the amount of free space. So this is basically the detail about the neural network architecture. So now, in order to do this, what we do is we have a neural network which takes a photograph as input, and it outputs not the 3D model, because working directly with the 3D model is difficult. So instead, it tries to put a predicted 2D picture. So if the photo looks like this, then how does the top view and the side view look like? So this is the top view picture for each shelf. So there are 3 shelves, so there are 3 pictures shown here. Similarly, there is a front view. So from the front, how do these boxes look like? What do these rectangles look like? So it is trying to estimate both of these given the input photograph, and from that it is able to estimate, because in order to get a 3D estimate, you need 2 things. One is what is the height and what is the width. And assuming that all of these are like rectangles, you can use that and the knowledge of the height of the rack to estimate the free space. So that is a basic strategy. And in order to make sure that we can have this method work for a lot of scenarios, we fill the warehouse. Remember that this is all synthetic world, graphics world. So we can fill this with different kinds of items. So here you can see that there are some soap boxes. Here there are some juice boxes, like large cartons. So it depends on us. And the more variety that we fill this with, so you can see that the colors of the racks are also changing. So this is the advantage with the doing this in 3D by using software such as Blender, because we can go beyond just the scenario of one warehouse. So we can develop approaches which work across different kinds of scenarios. So that is the advantage. So this shows the different kinds of warehouses and the items in the warehouse. Some more examples. So Parle-G biscuits, anything. So you can fill this warehouse. And you can also play with the number of shelves. So you can also change how empty a shelf is. A shelf can be fully packed, or it can be partially packed. There may be other shelves at the back. So we want a system which is able to handle all these kinds of challenging scenarios. And given this, it must be able to identify what is the amount of free space and how many stacks are there, right? So there are 7 stacks. So all of this information can be obtained just from the photographs. So these are some examples where it shows the different kinds of input image and the predictions and the 3D reconstruction. So these are from an actual scenario. So this is from a warehouse in Japan, and this is a warehouse that is in India, and it is able to figure out how much free space is there and how many boxes are there and so on. Yeah, so in order to do this, so how do we actually generate, like let us say that we are interested in doing this. So first of all, you get a 3D objects database. So these are available for free on the internet. And then you use a 3D modeling software like Unity, and you can use this. Instead of placing it manually, you can actually write small programs which let you generate this in a method known as procedural generation. So you can use this technique called procedural generation to change via just a computer script the number of racks you want, the height of racks, placement of items. Everything is flexible. And once you have the warehouse, then you simply can move a virtual camera in this 3D environment, and you get a lot of photographs, and that becomes your data. And because you know exactly what the placement is, you don't have to do separate labeling. All labeling is automatic. So that is the advantage of this approach. So you can apply this for many different kinds of situations. So you can obtain how many objects are there, what kind of objects are there, and so on. And the code and the data for this is available publicly, and it can be used once again if you're interested in this kind of application. Okay, so that brings us to the end of this presentation. Any questions? Should I?
Yeah.
So can you please look at the comments and let me know, because I'm
going to give the permission also, sir. Wait for 1 minute. I think they can interact with you also.
Sure.
Yeah, now participants, you can switch on your mic and you can interact with Professor Ravi Kiran S. if you have any doubts. Deepak Guria, you can switch on your mic and camera. You can interact with. You are asking a lot of questions. Please interact with sir.
Hope I am audible, sir.
Yes.
Yeah, I had a question on a real-time data. When you say drone or anything, when I mean a robot is moving and trying to collect the real-time data of images and all, right? For obstacle detection, friend foe detection, and to pick and place kind of it. So you have a lot of input of data coming, like because it's a video streaming happening continuously to identify if there is any obstacle or something once it is moving. So I wanted to understand, like, how would be the processing with respect to processing techniques of these algorithms to understand for a quick images which passes by when the video is streaming, or for a or sudden impact if any object is coming, to understand if there is a object detection and all. So what would be those type of image detection techniques over there?
Right. So there are typically the videos that are collected by using a camera-based sensor. They are treated in two ways. So one is to simply do processing with the image stream, but to not do any storage. So if there is no storage, then the only challenge will be how fast a particular method can work for your task of interest. And this can be useful particularly if storage is not practical, or you need to act immediately instead of working on stored data. But there are other scenarios where you have the luxury of time. So for example, either this warehouse or for detecting cracks. So there is no pressing immediate urgency. Of course, you want the methods to work as quickly as possible, but you can always record the data first, and you can do a lot of processing. So in order for this to work, you either have a storage system on the robot itself, right? So for example, the camera is connected to a laptop or some other motherboard, which allows you to record to, say, an SD card with high capacity, right? So it's a 2 terabyte or 3 terabyte, any kind of card that you may have. The other option is that the camera, the entire equipment, the drone, has a streaming processor. So like Wi-Fi, where it can take the images, transmit them to a base station, and all the processing happens on the base station. So if it is within the reach of the signal, then this is another practical approach. So usually, depending on the limitations of where the robot is deployed, these choices are kept in mind. Does that answer your question?
How are the algorithm? So how is the algorithm designed, and what is the programming techniques you use there? Like, is it any machine learning with reinforcement learning to understand a robot to take it, to check so and so happening or something with RL or something? Image processing, can it be combined?
Right. So there is a large variety of algorithms. So if you think about any robotic solution, typically there are, if you think about a robot, what are the things that a robot needs to do? One, a robot needs to be able to move. So therefore, you will have control algorithms which tell how the robot should move. Like, it sends commands to the wheels or to the arms to pick something or to move forward. Or to take steps and so on. The second is perception. Basically, needs to be able to sense the world, either by passive sensors like sonar or radar or laser, or you have sensors like cameras. So based on the input, some algorithm is used to turn the input into a control command. So if you see something, then move left, otherwise move right, and so on. So this usually forms the core logic. And apart from this, as the robot moves, it may, inside its memory, it may construct a map so that it can place itself. So somebody may supply a map, and it will try to use different methods to try to understand where it is on the map. So these are the usual kinds of algorithms that are involved. And if the task, again, depending on the task, the complexity of these algorithms changes.
How about for unknown terrain, sir?
I will actually show an example of that, and maybe that will give an answer. If not, you can ask a query again. Any other questions before
Yeah,
we
that's
move on?
Hello.
yeah. Yeah, please, madam, please. Madam, I think you are muted. Please unmute your mic and please. Hello. Yeah, you are muted. Please unmute your mic.
Sir, can I ask?
Yeah,
You
please.
put some code in a GitHub related to this image classification. So this code are means in which language you used, in Python or something else, and how is it possible to run means in a cloud this particular simulation using Python? So such type of means just to give me an input so that we can explore further this your research or related
Right.
to your
So I think
classification.
if you look at, so I can just share the, I can share the resources separately also, but you can look at Blender. So Blender is for creating 3D assets, right? So I'm just showing. I hope my screen is visible.
Yes, sir. Yes, sir. It is visible.
Yeah. So
Yeah.
Blender is what you can use to create 3D models. So if you just search for BLE and DER, that you can use. And I think other speakers may have already talked about ROS. So you can look at ROS library, and you can also find a Python version of it. And they will have some things which can be used directly. So it can interact with different sensors. It can even create simulations. So many people, they don't have access to physical robots, but there are a lot of things that you can do in simulation. So what it does is it gives you all these simulated worlds, and in that you can write code and test, right? So ROS simulator. So if you just search for simulators, it can give you different kinds of robots, right? So you can get simulators for walking robots, moving robots, and so on.
Thank you.
Sir, one participant is asking, what are the common challenges in future extraction for underwater localization?
For underwater localization, I am personally not familiar with the area,
Okay.
but I would think that from what my interaction, I have seen that sensing is a problem, right?
Yes.
Because inside the water, uh, the atmosphere can be very turbid, so you may not be able to see well. So therefore, you will need a combination of multiple sensors, not just a camera, but possibly sonar and all of this. And you have to somehow combine information from these multiple sensors uh, to be able to solve different tasks, either navigation or object identification and so on.
Yeah, participants, any other questions? I think
so over here I am showing some examples of ROS simulator. So if you search for ROS simulator, you can see how there are different kinds of robots, industrial robots and so on. And now without actually purchasing one, you can get a lot of, you can do all of this using computers. So all of these are readily available. So they are a good starting point. Yes, yeah, somebody had a question.
Yeah, please.
Sir, this is Selvam from Anna University, sir.
Yeah, please, please.
Yes, please go ahead.
Sir, my question is that here nothing that one of our participants asked the question regarding that for the prior knowledge based that environment, how we can able to detect the objects. So here my suggestion or my question is that here can you use a few shot learning kind of approach here, sir? So that the live tracking will be easy and such a way we can detect the obstacles also. It's a few shot learning.
Yeah. So few shot learning depends on the ability of the neural network to learn from very few examples.
Yes.
So it is difficult to answer in general. The method will rely on the quality of the examples that is being provided. So it's like with people, like, if you're shown 5 examples, can you learn the concept from just 5 examples?
Okay.
So it depends on the difficulty of the task and the chance of that object getting confused with something else. So these are some factors which will affect the problem.
Yes, sir. But here the environment what you are setting up is it will limited space, right, sir? Because the stacking the items in the row, and from
Correct.
that only we'll be able to. Yeah, so that's
Correct.
what I'm
So
asking.
basically,
Yeah.
yes. So now, if you want to identify an object, generally,
Yeah.
if you think about items that are coming into a warehouse, they will have some markers, right? So
Yes, sir. Yes,
you
sir.
can
Yes.
identify, say, something about. So even if you are not able to identify the brand, you will be able to identify maybe the lettering. Say that this is shampoo or this is biscuits and so on, and from
Okay.
that you can tell something.
Okay, sir. That means the labeling must be proper here.
Yeah, labeling information can be used, and also many items they will have batch number, barcode, and all that. So you can use techniques like OCR to read them and try to understand
Yes,
what
sir.
they are.
Yes, sir. Yes, sir. Thank you so much, sir. Thank you so much.
Okay, so shall I move ahead?
Yeah. Thank you, sir. Thank you for your session. Yeah, you can leave,
All
sir.
right. Yeah, so let me move to the. Yeah. All right. So shall I stop the sharing?
Yes, sir. You can stop it, sir.
Sir, can you hear me,
Okay.
sir?
Somebody want to ask some questions, maybe.
I think sir left.
Yes, sir. Yes, sir.
Sir left.
Sir,
Sir
I
is
am
there.
Mohan
Sir
Raj.
is there.
Ravi Kiran, sir.
Sir is there.
Yes,
Can you
yes.
hear me, sir?
Please. Please, Deepak Goria.
Yes, sir. Can you suggest some tools for simulation, like static and dynamic simulation of
Static and dynamic simulation of, I missed the last part.
robot components, something like maybe the movements of hand and forearm.
Yes. So I think you can try to look at, as I was mentioning, you can try to look at draws. So I am posting a link. You can just look at that. And if you follow some of the links over there, you should be able to find that. So you can use that as a starting point. That may help.
Thank you, sir. Thank you so much.
Thank you, sir. Ravi Kiran, sir. Thank you for accepting our request.
Yeah. Thank you.
Thank you so much, sir.
Thank you.
Yeah. So bye and good night, everyone.
Yeah. Bye.
Thank
Good
you.
night,
Thank
sir.
you. Thank you.
Yeah, participants, please wait. I think please wait. Don't leave the meeting. Ravi Kiran, sir, you can leave the meeting. Yeah, I already shared the Google Sheet for attendance and at the same time for feedback. Participants, please fill that Google form before 10 p.m. by today only. Okay, and it is shared in Microsoft Teams chat. Okay, and we will not share in WhatsApp group. And those who are attended, they can easily download that Google Sheet and they can fill the form. Okay. Yeah, you go back and check it. It is there already in the Google chat, and check it in the Google chat. Yeah, once again I shared. Please try to fill your attendance and your feedback. Okay. Yeah, I already resent, I think. Yeah, thank you. Thank you for attending this session. I think you hope you are enjoyed these sessions, like Professor Engsin Kim, and at the same time, I think Dr. Ravi Kiran S. Okay, you can leave the meeting now. I'm going to end the session. Please, thank you.
Okay, thank you, sir.
Yeah, please.